So in this video, I'm going to discuss homogeneous as well as heterogeneous equilibrium and how Le Chatelier's principle can be used to determine what would happen to a system that was at equilibrium but encountered a disturbance. So let's start with equilibrium. Recall equilibrium indicates that the rate or speed of the forward reaction is equal to the rate of the reverse reaction. We know we're dealing with the reverse reaction if we see the double-headed arrow. So that arrow going in both directions indicates that the reaction will also proceed in both directions. From there, we can look at the physical states of everything that is present. If we only have one physical state, that represents a homogeneous mixture. So when you see the prefix homo, that generally indicates one. So we only have one physical state present. And so we have a homogeneous mixture, or excuse me, a homogeneous equilibrium. And so from there, we can determine our equilibrium expression. Recall K or KEQ, whichever way you want to look at it, they mean the same thing. That expression tells us that we're dealing with the concentration of products divided by the concentration of reactants. Now, although this reaction is reversible, we're talking about the forward reaction, so from left to right. So with the forward reaction, these are my reactants to the left and my products to the right. So keeping that in mind, we can then determine how to set up this expression. And so for our K, our products, we only have one, which is SO3, but there are two SO3 present. So you can imagine SO3 times SO3. Since they're both in the gas phase, they would be included. There are two physical states that you include with equilibrium, and there are two that you exclude. The gas phase, you do include. The aqueous phase, you also include. You exclude solids and liquids, so pure liquids. So in other words, even though they may be in a liquid phase, if they're aqueous, meaning that they're mixtures, that's not a pure liquid. Pure liquids mean you only have that one thing present. It's a pure substance. But in this case, we have only the gas phase present. So all of these would be included. So we have both of our products, they're both the same. And then for our reactants, since they're all in the gas phase, they would all be included as well. So we have two of those SO2 molecules, so both of those would be included. And we have the O2 molecule. But if you notice, just like in math, when you're multiplying the same thing by itself, instead of writing it out more than one time, we can simply show exponents. So we could have written this expression as SO3 squared, because we had two of them, divided by SO2 squared, because we had two of those, times O2. So if you notice, your exponents correspond with the coefficients that were present. So when writing out the expression, you have your products over reactants. If multiple reactants or products are present, multiple of the same, that coefficient becomes your superscript, so your exponent. And so this is our equilibrium expression. When dealing with the equilibrium expression, everything that's provided, any change to any of those substances could affect this system at equilibrium, which would then apply Le Chatelier's principle. So if we look at another example, now we have another reversible process, and again we see our reaction arrow going in both directions. So I know that I'm dealing with a reversible process, meaning that equilibrium can be achieved. Now, this reaction that I'm showing, I showed the physical states in the normal format, whereas the previous reaction, I showed them as subscripts. I'm doing this to show that it doesn't matter which way you see them. You can see them either way. They still tell us the same information. We simply put the S, L, G, or AQ in parentheses immediately following the formula for that atom or that compound or that molecule. And so now, because we know that we're dealing with the reversible process, we know equilibrium can be achieved. However, when we look, we have a solid phase, gas phase, another solid, and another gas. So now we no longer have simply one physical state present, but instead we have multiple. So this is an example of heterogeneous equilibrium. So homogeneous equilibrium simply told us one physical state was present. Heterogeneous equilibrium indicates that more than one is present. Everything else is still the same. It's still products over reactants. From there, we still have to look at which products or which reactants we include as well as which we exclude. And so because we have the solid phase now, recall solid phase is excluded. So we would not include that in our equilibrium expression. I put the X above the formula. If you want to just cross it out altogether, you can, because we're not including those. Pure solids do not affect the system at equilibrium. They remain unchanged. Just imagine if you're putting a table in a pool versus putting a table in the ocean. It remains unchanged because it's a solid. So it doesn't affect what happens. If we add another table, it's not going to affect what happened to the first table. And so when we're dealing with solids, they remain unchanged, so they do not affect your system at equilibrium. We do include the gas phase, and again, we include the aqueous phase. We don't have aqueous present in this one. We only have the gas. So those are the only ones that will be included in our equilibrium expression. Again, we still have products over reactants. So only one product is included, which is our CO2. Only one reactant is included, which is our CO. We only have one of each, so this equilibrium expression is simply the concentration of carbon dioxide divided by the concentration of carbon monoxide. So changing the amounts of either one of those substances could cause Le Chatelier's principle to kick in, which means that the system's equilibrium has been disturbed, and now it's going to react in order to again achieve equilibrium. So we'll talk a little bit about Le Chatelier's principle as well. So again, Le Chatelier's principle tells us that when a system is at equilibrium, if there is a disturbance to that system, the system or reaction will then react in order to balance out that disturbance. So in other words, it's trying to again achieve equilibrium. So depending on what the disturbance is, that determines how the system changes. So here we have this reaction. You're shown all of the products, you're shown the reactants, you're shown the physical states, and you're also shown the heat. So a couple of things to keep in mind. One, because we have multiple physical states here, we are dealing with a heterogeneous equilibrium. In order to determine what will or will not affect the system at equilibrium, we could start by establishing the equilibrium expression. So we could start this by determining what our K would be. So again, K is products over reactants. We have aqueous, that product would be included. We have the gas phase, that product would be included. We have on the reactant side, the gas phase, so that one would be included. And then we have the liquid phase, it would not be included. So that means that this equilibrium expression will be equal to the concentration of C6H12O6 times the concentration of O2 raised to the 6th power, because I have 6 of them, divided by the concentration of CO2 raised to the 6th power, because I have 6 of those. So any of these substances that are in this equilibrium expression could affect this system at equilibrium. So in other words, changing the amount of the C6H12O6, changing the amount of O2, changing the amount of CO2, all of those could change how this system behaves. Even changing the amount of heat could change how this system behaves. But let's think about what happens. So here I'm showing you a seesaw. So I like to think about a seesaw when talking about Le Chatelier's principle. Of course, if you think about a seesaw, if there are equal amounts on both sides, then the seesaw is balanced. So what you're looking at right now is a balanced seesaw. That is going to represent our equilibrium. So once the system is at equilibrium, we can just imagine that everything is balanced. Doesn't mean that we have to have the same concentration or same amount of reactants and products, but it tells us that the rates of the reactions are the same. So we're just going to use the seesaw to simulate what happens. So let's just imagine that we decided to add more carbon dioxide to this reaction. So if the system was at equilibrium and now we wanted to add more reactants. When we add more reactants, we're disturbing this balanced seesaw. So by adding more reactants, the reactant side gets heavier. Now it has more present. Our seesaw is no longer balanced. The way the seesaw works, the side that moved up indicates the direction that the reaction has to shift in order to again achieve equilibrium. So right now, the reactant side went down, the product side went up. So we would have to shift in the direction of the product in order to, again, achieve equilibrium. So how do we shift towards the product? So by adding more of the reactant, what that means is that now the reaction can occur. It can continue occurring. So as more reactants are added, now that the reaction can occur more, those new reactants are going to be consumed while we're producing or generating more of those products. And so as the reactants are being consumed or used up, that side starts to feel lighter, so it starts to increase. But at the same time, we're generating more products, so that side begins to feel heavier. So in other words, it starts coming back down. So this process occurs until, again, equilibrium is achieved. So if we were to go through and this system was at equilibrium and we decided to add any of the reactant side that would affect equilibrium, it's going to cause a shift to the right in this reaction, meaning that we're going to form more product. So you can hear that it's shifting to the right or it shifts to the product. And so it's not just for this system, that really applies for any system. If the reactant affects the equilibrium, so if it's present in that equilibrium expression, by adding more of that, it's going to shift to the right. But what if we wanted to add more product? So now both products will affect the system at equilibrium. So again, if we're starting with the balanced seesaw, but now we decide we want to add more of the product, so we want to add more of this C6H12O6, or we want to add more of the oxygen, again, think about what happens to your seesaw. Now the product side feels heavier, so it goes down. The reactant side now goes up. So what this means is that because we're adding more here, so we're adding more to this side, it's going to cause us to produce more reactants. So it's going to have to shift to the left in order to, again, achieve equilibrium. When it shifts to the left, it's shifting towards our reactants. So once we add more of either of those products, product side goes down, reactant side goes up. To again achieve equilibrium, it has to shift back to the left. So when it shifts back to the left, we're going to use up those added products so that we can then form more of our original reactant. So by adding more to the product side, we're going to see a shift in our reaction. And so just as we can see what happens when we add more reactant or we add more product, we can do the same thing with removing reactant or removing product. So let's say I wanted to remove some of the CO2 that was present. When that happens, that side gets lighter. So the reactant side, because that's where it's located, that side gets lighter, causing the other side to feel heavier. And so the same process, whichever side goes up indicates how it would shift. So removing, do a different color. So for us to remove the reactant, I'm just call it R. Removing the reactant results in a shift to the left. And we can do the same process if we wanted to remove the product. In that case, the product side gets lighter. The reactant side feels heavier, so it will shift to the right. And then we can also look at this process with regards to heat. So depending on whether or not it's an endothermic or exothermic reaction, that determines whether or not heat is treated as a reactant or a product. If you're dealing with an endothermic reaction, heat is treated as a reactant. So endothermic, we can just imagine that heat is entering the reaction. So it's on the reactant side. And so depending on whether it's endo or exothermic, that determines which side you're placing the heat. And then from there, if you're adding or increasing the temperature, or you're lowering or decreasing the temperature, you just go from there. So if we have this endothermic reaction and we want to increase the temperature of the reaction to determine what would happen, if we're increasing the temperature, that means that we're adding more heat. And because heat is on the reactant side, if we add more heat, The reactant side feels heavier because it's like we're increasing the amount of reactants. So it simulates that same process of adding reactants. Because the product side went up, it's going to shift to the right to generate more products. So endothermic reactions, by increasing the temperature, is going to result in a shift to the right. So it's going to shift to form more products. So the previous reaction represented a heterogeneous equilibrium. This reaction that we're looking at now represents a homogeneous. But it doesn't matter whether or not your equilibrium is homogeneous or heterogeneous, the process works the same way. And so think about the seesaw. Think about whether or not you're adding or removing reactants or products. That determines how your seesaw changes. Again, whichever side goes down, it's going to then shift in the direction of the opposite side, the side that went up. The only difference that we can think of when talking about equilibrium is whether or not we're dealing with an endothermic or an exothermic reaction, because that dictates whether or not heat is treated as a reactant or a product. So in the previous example, we were looking at an endothermic reaction. Endothermic reactions, heat is treated as a reactant. Exothermic reactions, heat is treated as a product. So we could think about it as the heat exiting the reaction. And so again, once you know your reaction is endo or exothermic, that tells you where to place your heat. From there, everything else falls in line. Think about what changes can be made, how it affects your system at equilibrium, and then that determines how that system would shift. So here we have this homogeneous equilibrium. So I'll go through and still show the equilibrium expression just to make sure you're good with that. So our K is still products over reactants. Because everything is in the gas phase, everything would be included. So we only have that one product, NH3, but that 2 is a coefficient, tells me that I have 2 of them, so I have to show that as my exponent. So NH3 squared. I include both reactants because, again, they're both in the gas phase. So N2, there's only one, so I just show that once. But then I have H2, however, it has a 3 as the coefficient, so that 3 becomes my superscript or my exponent. And so because everything that's in this reaction as a reactant or product is present in the equilibrium constant, that means that changing the amount of any of these substances will affect the equilibrium. So we've already gone through and looked at what happens if you increase or decrease your reactants or products. We talked about affecting or changing the heat of an endothermic reaction. So for this one, we'll just focus on changing the heat for an exothermic reaction. And so again, exothermic means that heat is treated as a product. So with this reaction, if we wanted to increase the temperature of this exothermic reaction, by increasing the temperature, that means that we're adding more heat. Since heat is on the product side, we're adding more heat on the product side. So that side of the seesaw goes down, the reactant side goes up. Again, it's still shifting in the direction of whatever went up. So by increasing the temperature of an exothermic reaction, it's going to cause a shift to the left towards the reactants. So any exothermic reaction that is at equilibrium, increasing the temperature causes it to produce more of the original reactants. Of course, if we looked at decreasing the temperature, then we're going to see the opposite. So again, the temperature increase causing a change in our seesaw to shift it out or to bring it back to equilibrium, it shifts back to the left. But if we wanted to look at decreasing the temperature of an exothermic reaction, we can think about that as well. So if we lowered the temperature of this reaction, again, because it's exothermic, heat is a product, so by decreasing the temperature, so if we lower that temperature, now our product side feels lighter, reactant side feels heavier, so now the reactant side goes down, product side goes up. And so again, the reaction will shift in the direction of what went up, and so because our product side went up, it's going to shift to the right, towards the products. So by decreasing the temperature of an exothermic reaction, it causes more products to be produced. So this is how you would determine whether or not equilibrium is homogeneous or heterogeneous, as well as how Le Chatelier's principle can be determined and indicates how the system would, again, balance itself back out to achieve equilibrium after a disturbance was made. I hope this helps. If you have any questions, please let me know. Thank you.